Our next speaker is Damien Eggermont, and he's going to talk about some profiling of volatile organic species in honey. Damien, the floor is yours.
Thanks a lot for the presentation, for the introduction. So I will directly start by talking a bit about honey and especially about the 5-hydroxymethyl furfural. So the question here is, why do we have to analyze these compounds? So this is a compound that is produced during heat processes and with the time. So it's a global indicator of freshness of the product. So the maximum content of this compound is legislated by the European Union, but also in the USC legislation, for instance. And so the general limit that are well known is 80 milligram per kilos and 40 milligram per kilos. But European legislation had also a limit of 15 milligram per kilos for low enzyme activity honey, such as thyme honey. So all in all, that means that we have to develop analytical method that can reach these limits. So our first objective is to develop this targeted method to assess the freshness. So you can say, okay, that's really great. It's kind of boring because we already have this through the official method. But here we are using a GC times GC mass spectrometry that can give other compounds and other information that can be used after for untargeted analysis that can answer to different questions such as authenticity, botanical origin, contaminant, and so on. So here, what is different from the method that we would like to develop versus the official one is that we have multiple response that we can give and not just one that is here, the freshness. So regarding the sample preparation, so we are using vacuum-assisted SPME. So it's the regular headspace-SPME that is well known, but for which we put the vial under vacuum. The effect of the vacuum is to decrease the resistance to the mass transfer in the gas phase film. So if we have a closer look at the interface between sample and headspace, there is two phases, and so the vacuum will decrease the resistance to the mass transfer in the upper part close to the headspace, which in all will increase the overall mass transfer from the sample into the headspace and also faster the equilibration time for the low and semi-volatile compound. And since HMF is it's considered as a semi-volatile compound, here we are expecting that the use of vacuum will be beneficial. Regarding the instrumentation, so we will use Sentry as sample preparation, GC times GC using an apolar and a polar column, and quadruple mass spectrometry. So our first trial, we see that the HMF was really tailing in the system, meaning that we were not able to integrate and to have an accurate integration for quantification. So we had to derivatize, so we did a non-fiber derivatization with BSTFA. So we had, of course, to optimize it. So we use a central composite design for the time and the temperature. What we observe is that the temperature was leading the derivatization step. And so we derivatize for 5 minutes at 80 degrees. We also optimize the extraction. So here we use the Duller design, that is an hexagonal design. And compared to the other one, this one has the possibility to be extended in many directions by reusing data sets that were already done. So here we use this because we wasn't sure about the optimum, if we were close to the optimum or not, with the range that we studied. And here, what we observe is that the time, temperature, but also the interaction was significant. So we reach an optimal at 17 minutes of extraction, 60 degrees. So this is the overall method. So first step of weighting. Then we have a freezing step that we use to decrease the volatility of compounds present in the sample to avoid the loss of them during the step of vacuuming. After there is the extraction, derivatization, and then the fiber desorption. The 4 last parts can be automated, whereas the first one, unfortunately, dealing with sticky matrix such as honey, it's a bit more complicated to automatize. So we validate the method through a matrix match calibration at 5 level. Regarding figure of merits, we see that we are fine regarding SPME method. And for the limit of quantification, we are 3 times below the targeted limit that we wanted to reach. We trialed the method with 6 diverse real-world samples. We analyzed them, one with our method, and also with the official HPLC UV method. That is the direct injection after dilution of honey into the HPLC. One thing important here is that since HMF is not really stable in aqueous solution, if there is a delay of more than 30 minutes between the sample preparation and the injection, we have to add a keeper solution, so here carré solution. So here to avoid adding this, we managed to do everything below 30 minutes. So what we can observe from the comparison here is that we are in agreement with the official method. There are just two samples that are not in agreement, but they are below the LOQ that are already far below, 3 times below the limits asked by the legislation. So I talk initially also about the different compounds that we can extract, and obtain with the method. So here I will focus more on the untargeted parts. So as I already show here, we can, if we compare the vacuum and the atmospheric extraction, so we can see that, okay, we are extracting the 5-HMF here, but in a smaller amount compared to the vacuum one. But we can also see, first of all, that the vacuum extraction can extract much more compounds, and also with a higher intensity. We can extract more with a shorter time than the regular atmospheric. So here we wanted to have a closer look, a more in detail look at the performances here. And so we plot here the area ratio between the vacuum and the atmospheric extraction. So the size of the bubble represents the ratio. So to give you an idea of the scale, the bubble of the legend is around 1. So, and if the bubble is green, that means that the vacuum, the area coming from the vacuum extraction is lower or equal to the one of the atmospheric, the atmospheric, sorry. So we have here a first part on the early eluting compounds, the early eluting part of the chromatogram, where vacuum doesn't have a great impact, and this is something that is already known because since vacuum is increasing, is accelerating, sorry, the extraction of the compounds. If the compound is already volatile enough, that won't change the quantity that we will extract. Whereas on the late eluting part, we can see here that we extract much more with the vacuum. And this is particularly interesting to couple the vacuum with GC-GC, because if we extract much more compounds with a higher intensity, we need to have an increase in separation. So for this, GC times GC is perfect to solve this. So the last part here is to compare the green performances of both analyses, so I will do it shortly. So globally, our method was slightly better than the official HPLC method, and we were penalized because we use GC-qMS, GC GC-qMS, and also because we derivatized we had to use a derivatization step. But we just would like to emphasize the fact that we are using 50 microliter for 20 samples. So for us, the derivatization is not as problematic as the metric seems to show. Then also we answer to more questions than the official method that deal only with the freshness of the honey. So that's all for me. I will just finish by saying that this project has been recently published in Green Analytical Chemistry, and so I would like to thank you for your attention.